Hello everyone, I am Zach Peterson. Welcome back to my channel, and today I am very happy to be answering your questions from all of my videos on Altium Academy. This has been a great series and I'm glad you're here with me, so let's go ahead and jump into it right now. Now this first question we're going to look at comes from one of the 1-minute design reviews. This design comes from Richard Andreak, and the question is, why do we need copper balance? Now this is a great question, and I think it relates to the usage of copper pour, but not for the reasons that a lot of designers will use copper pour. One of the biggest reasons that designers will use copper pour is because they start with 2-layer boards and they need the copper pour to provide ground. And then when they try to scale up to 4 or 6 or 8-layer boards, they just keep using the copper pour without thinking about why they were actually using it. Copper balance refers to the use of symmetric amounts of copper in the top half and bottom half of the PCB stack-up. And that's basically what copper pour is doing. If you look at a 2-layer PCB, when you have copper pour up on the top layer, you also want to pour copper on the bottom layer in order to balance the copper. So we have about the same amount of copper on the top side as we do on the bottom side. This same idea extends all the way up to as many layers as you have in the multi-layer stack up. It's just that you want to make sure it's symmetric distribution of copper in the top half versus the bottom half. The main reason we do this is to prevent warpage. It helps ensure that the heat distribution in the top side and the bottom side of the board is even as the board is pressed into a stack up, and that will help ensure that warpage stays very low, below the standard that you specify in your fabrication notes. This next question is all about applying ESD protection on RF lines, and it comes on another one of our 1-minute design review videos. Here the question is, what if ESD protection is needed? What would be the right approach? So just for some background here, in this particular 1-minute design review, the designer, Christoph Schmid, originally used a TVS diode on an RF line. Now, it's not that you can never use TVS diodes or any other kind of ESD protection on an RF line. It's just that in this case, I prefer to not use TVS diodes, especially once you get to very high frequencies. There are some TVS diodes that are operational at very high frequencies, all the way up into the Wi-Fi range. Typically at the range that was used in the design review, which was GNSS frequencies, you're still going to be able to find TVS diodes that are going to be acceptable in that range. But in those frequency ranges, going from, let's say, 1 gigahertz up to 6 gigahertz, you're going to have to accept a little bit of attenuation, and that's due to the capacitance across that TVS diode. So that capacitance allows a little bit of signal to pass into ground rather than passing over to an LNA or a filter and then into your receiver. Now the other thing to think about when using TVS diodes is the fact that they are nonlinear components. And because they are nonlinear components, they can create harmonic generation. Now harmonic generation is not necessarily a problem if you're just dealing with a harmonic signal, because harmonic generation generates new frequencies at multiples of the fundamental frequency. It does matter when you have a frequency modulated signal. When you have a frequency modulated signal, you get what are called intermodulation products. And those intermodulation products are basically multiples of integer differences between the two signals that are used to create your frequency modulated signal. So we'll probably do another video on that soon. But the reason that's important is because you can get sideband generation that then falls within the channel bandwidth where you're trying to transmit your desired signal, and that can create a lot of data errors. So I prefer to not use TVS diodes on RF lines when you have a frequency modulated signal. Now this next question comes on one of the older but better videos from Altium Academy. This one is all about alternative 4-layer PCBs, and in particular the use of signal ground signal stackups. Now I think one of the commonly used stackups is signal ground power signal, but I think a better stackup for most high-speed designs is signal ground signal. And the question or the comment is, for real-life boards, it is simply a nightmare not being able to connect two components with a simple trace on outer layers where they are placed. I mean, you should go through vias every time. That stackup is purely academic, not worth considering. Just go to 6 or 8 layers if you have high-speed traces. I have to say, I totally disagree with this comment. When something is manufactured at volumes of millions of units per year, it's not academic. Vias were also mentioned, and frankly, the use of vias is just fine on high-speed signals as long as your channel bandwidths don't exceed approximately 3 gigahertz. You'll still have really low return loss, and you don't need to worry so much about designing those vias to have a very specific impedance value. That applies for both differential and single-ended signals. That's why you're able to use vias on interfaces like SPI without any problems with signal integrity. Now, there may be some reflections at the very high end of the frequency range, but it's not so much that you have to worry about EMI, particularly if you use the Stackup that is mentioned in this video. So go take a look at this video if you want to learn about the right approach to Stackup design on 4 layers for high-speed PCBs. This next question comes from one of our older videos about defining ground in mixed signal PCBs. Here, the question asks, we connected 2 ground planes through a capacitor, particularly a Y-type capacitor. Will it create a problem in EMI/EMC testing? First things first, the use of a Y-type capacitor to connect 2 separated grounds is generally done in DC-DC converters. The reason you do that in isolated DC-DC converters is so that you give high-frequency return currents on the secondary side a chance to travel back to the primary side, and then they can complete a circuit with the ground return on that input power connector on the primary side. The reason you do that is so that those high-frequency currents don't radiate from the secondary side. So the use of the Y-type capacitor to prevent radiated emissions is recommended. It is a good practice, and Y-type capacitors of various sizes can be used. You just need to make sure that you have the right galvanic isolation value that you're targeting for your particular design. Now, one of the issues with Y-type capacitors is that you could have leakage current through the Y-type capacitors at lower frequencies. Now, that is a problem because some devices, for example, medical devices, have limits on the allowed leakage currents, and that's done for user safety. So you have to balance the need for suppressing radiated emissions using a Y-type capacitor with the leakage current that you could experience from that Y-type capacitor. And there may be a happy medium that you find. You may be able to find a low leakage current Y-type capacitor and then maybe apply some shielding on the enclosure to help suppress any leftover radiated emissions at high frequencies. Speaking of Stackups, this next question is also about Stackup design, specifically the signal-ground type of Stackup in a 4-layer PCB. Question asks, hi Zach, thanks for all these videos. To help prevent EMI and EMC problems, lately I've been using the signal-ground, or sometimes signal-ground signal Stackup. I prefer to route power on a signal layer rather than on a plane. In this case, I will have all signals on power referred to the ground plane. Is this the correct approach? Yes, this is the correct approach as long as you don't have high current. One of the reasons that we might use a power plane in a 4-layer Stackup, such as signal ground power signal, is because that power plane needs to carry a lot of current. Another use case is when you have 2 different rails that also need to carry very high current, but it doesn't make sense to put them on your component layers because there might not be enough room to provide enough copper. You could then use an individual layer for both rails and then put them side by side, route them wherever you need, and they'll be able to handle the current that you need to deliver to your components. Now in this case, you also get some good protection from EMC problems because you have a ground layer right next to your signal layer. So the way you're using these non-standard Stackups like signal ground is perfectly appropriate. Go ahead and keep doing it. And of course, if you have a design that we can look at in a 1-minute design review, make sure to send it to me on LinkedIn. Now, for those of you who have been paying attention to the new features in Altium Designer, you're probably aware that there is now a wire bonding feature. I think this is a really cool feature because it automates a lot of the aspects of defining the 3D modeling that's used to show wire bonding in a PCB. It also automates some of the placement of, for example, those pad arrangements that you would see in a wire bonding footprint. This next question comes from the Advanced Wire Bonding Techniques video in Altium Designer that was produced by the product marketing team over at Altium. When adding wire bonds from the PCB layout rather than defining the pads within the component, is it possible to update the schematic layout with the updated netlist? Would be nice to have this so that the IC pinout is directly included in the PCB schematics. This is a really odd question, and it's asking about the bidirectionality of basically automatically updating something in the schematic based on something that you added later in the PCB layout. That's not really how it works. The way it works is everything is driven by the schematic. So if you want to make a change to something in the schematic, you have to start there. And it really all starts in your libraries. So if you want to add pads to a wire bonding footprint, highly recommend that you go back to the original footprint in your libraries, do the update there, and then import that change into the PCB layout. That doesn't just apply to wire bonding components, it applies to all components that you use in your PCB. This next question comes from one of our videos from earlier this year, and it's all about using a VNA to measure trace impedance. Now, we did a little demo using the Libre VNA, but of course you could follow the same steps with a different VNA like the Nano VNA or a much larger VNA. Of course, those are very expensive instruments. The question here asks, hello, I have a question concerning your video. The primary question was how to measure the trace impedance, but I could not find any concrete formula how to do this using S21 and S11 in the video. Could you please provide the exact formula? Thank you. Well, here's the thing. It actually requires two formulas. It doesn't just require one formula. Now that's very important. What the S11 term is measuring is it is measuring the reflection coefficient. And the reflection coefficient is the reflection between the input impedance at one of the ports and the impedance of the cable connecting to that port. So in this case, we're dealing with 50 ohm cables, so we're reflecting between an input impedance that's near 50 ohms and a cable that is exactly 50 ohms. Now you can take the reflection coefficient and solve for the input impedance, very simple. Then once you have the input impedance, you can solve for the characteristic impedance of that transmission line on your test PCB. That's also very simple. Now, this again assumes that you are terminating that transmission line to the 50 ohms of the other cable that's being used in the VNA connection. Because remember, a VNA is a two-port instrument, and you're connecting two 50 ohm cables at each end of that transmission line. Now, you could also just terminate the other port on that test board to exactly 50 ohms, or you could terminate it to open, or you could terminate it to short. It doesn't really matter. As long as you use that termination load in the input impedance formula, you can solve for the characteristic impedance. So I'll make another video about this in the future. Make sure to subscribe and you'll get an alert when it's ready. This next question comes from our video about V-scoring and mouse bites. This question asks, just a heads up, board cutouts do not export in Gerber output. Another setting under line and arc primitives from board shape must be set to a mechanical layer to outline the cutout for proper recognition by the PCB fabricator. So not really a question, but you get the point here. What I can tell you is this, at least in Altium Designer, board cutouts will export as long as you enable the board outline option in the fabrication outputs dialog. So make sure to check out the documentation to see what I'm talking about. Now, you can, of course, create a mechanical layer, and that mechanical layer could have the board cutout defined in it, and then you would have to export that and send it to your fabricator along with the rest of your Gerber data in order to show where the board cutout is. You could also then indicate where the cutout is using your fabrication drawing. You can then show the dimensions, you can show the tolerances, everything that the fabricator needs to know to fabricate that cutout. But it is true, you can include the board cutouts in the Gerber export. Just make sure to enable that board outline option in the fabrication outputs dialog. Now, we don't get a lot of questions about flex PCBs, but we did on this video, on the video about designing bending regions into a flex PCB. We got this question regarding the definition of a flexible part as rigid for the purpose of 3D locking. How will this work for a flex ribbon that is bent into a circle with no flat parts? That's a really great question. I'm going to be honest here. I have never designed a board that was intended to be bent totally into a circle, and that's a really interesting type of design. And if you look back at some of the older versions of Altium Designer, there is actually an example board. I think it was designed by Ben Jordan, and that example board includes flexible strips which also wrap around into a complete circle. So I'm going to be honest, I'm going to need to do some research on this. If you hit that subscribe button, you'll probably see a video of me showing this in the future. You can also go over to Altium Academy, hit the subscribe button, and we'll do a demo over there. And our last question of today also comes from the designing bending regions into flex PCBs. This question asks, one issue I have is that when changing any board shape or outlines, all the flexible setup gets deleted. The rigid flex and bending regions, the lot all vanish. I'm sorry about that. A lot of extra work is required to redo it every time a small change is made. Is there any way around that? Well, I'm not sure why that's happening, and I would have to try and reproduce that problem. Now, I will say this. It is a good practice to first draw out all of those regions in a mechanical layer before you put them into the board outlines and then define your individual regions. The reason is that, of course, if they do happen to vanish, you can very quickly redraw them. You can just use the snap tool onto those mechanical points in your mechanical layer, and then you'll be able to redraw all of that out pretty quickly. Now that means if you want to do any updates to any of the board shape or board size for any of those regions, you would want to also do that in the mechanical layer for that same reason. You can then just snap onto each of those points in the mechanical layer and redraw it in the board planning mode once you finish your update in the mechanical layer. That's all I've got for today, folks. Thank you so much for showing up, and of course, thank you so much for all your questions on all the videos on Altium Academy. Make sure to head over to Altium Academy, hit that subscribe button. If you like these videos, make sure to hit the subscribe button here on my page, and we'll see you next time. Thanks, everyone.